All right, gang, we got our data into R. So again, we're conducting a repeated measures design. Um, and let's just dive in. What I would want to do at this point is I would probably want to take a look at the means across for score across measurement. So I would use the t apply, and I'd probably want to also look at the standard deviation with mostly emphasis on the means. And at this point, what am I predicting? Well, I'm predicting there's probably a difference between the pre and post test, and very likely there's a difference between the pre and the mid term test. But I don't know that yet. So first thing I may want to do is look at a box plot of the of just the score. Uh, Pretty boring, very non-entertaining, and I would say mostly irrelevant. The focus here is to examine the score over, of course, the measurement. Now, when I look at a box plot here, a couple things. I think of a box plot, again, these dark lines are the median. Our focus is not on the median. We're not running a non-parametric test. Our focus is on the mean, but remember, in a symmetric distribution, the mean and the median will be pretty close. So again, I'm taking a look at that. The next thing I'm looking at is outliers. Outliers can really cause some issues with repeated measures ANOVA, and outliers, of course, are denoted by points, and we do not have outliers. Now, let me show you a procedure that we could use to identify outliers, both what I would call extreme and mild outliers. We can, let's see, how do we do? We can access the R stat IX um, package. That doesn't look right. Yeah. So keep in mind, I've already installed this package, so all I have to do is just access the library. And what I can do next is I can do kind of a strange command, if I can recall how to do this. Um, so I want to group by the measurement. And again, kind of a strange command, something we see when we start, or something similar when we start manipulating operations on matrices. And then I want to do identify outliers for the score. And what this will do, and again, we don't have any outliers, so we, or I should, yeah, we have no outliers across score across measurement. But if we do, what it'll give us is it'll give us a row. It'll give us the measurement, it'll give us the score, and it'll give a true or false response for is it an outlier and is it extreme. If you have anything out here that's extreme, you want to give a lot of thought to deleting that observation. In fact, I don't even know if you'd really want to give a lot of thought to it. I think you'd want to be a robot and just do it. Okay. Um, so there are no outliers, and obviously there are no outliers that we call extreme outliers. Next thing I probably want to do is run Shapiro. So I want to test for normality. So I would run again t apply. I'll tell you what, let me just go up and get it and just run Shapiro test. And what this does, it gives me the Shapiro test for each of the measurements, the pre, post, and mid. And I examine the p-values. All the p-values are above 0.05, so normality is not a concern for me in this data set. Next thing I want to do is check equal variance. And recall to run Levine, I need to access the car library. So Levine test, and we want score over measurement. All right, so Levine's test comes back non-significant. So again, the null hypothesis here is that that we come the distribution. I'm sorry, that we have equal variances, and we fail to reject that. So no concern for the equal variance assumption. Now we get into the good stuff. All right, so what we'll do next is we'll test for sphericity. Make sure that's spelled correctly. That would be kind of embarrassing if it wasn't. And what we have to do here, we get in running this command, we'll not only get the sum of squares, the ANOVA output for the repeated measures, but we'll get some the information about the test of sphericity and some other options if the test of sphericity is violated. So we need to install and access the EZ package. So I've already installed it, so all I have to do is just access that. And the next thing I'm going to do is I'm going to run my model, and I use what's called the EZ ANOVA command. First thing I enter is the name of my data set. Next thing I will enter is strange the way we do this, but it is what it is. We'll enter the dependent variable. The next thing we do is the within ID, and that's just the subject. Just make sure that that is what where are we here? Yeah. And then I'm going to add the within factor. If I get all this type without a typo, it'll be amazing. And then I want a detailed output. And I want to type 3 sum of squares calculation. Let me just look back over that and make sure. Well, I'll tell you what, I'm just going to go ahead and run it. If I have a an issue, it will tell me. All right, I did have an issue. All right, so I need the within. Let's see, I do not need that. And I need, yeah, this should do it. Now it's converting subject to a factor, which is okay. Most warnings, we flip out over, but this is not one. Now here's a situation. I'm going to show you what happens. You don't want to do this. We usually just type in summary model, but for the EZ ANOVA, you don't. It gives you a meaningless output. I don't know if it's meaningless or not, but it doesn't tell us what we want. So all you do here is just type model. Now, we get into quite a bit in this output. All right, so let's try to make heads or tails out of what we get there. So the first thing we get in the upper part is we get the sum of squares for the ANOVA for the repeated measures design. The second thing we get is we get the Monkley's test for sphericity. If this test is not statistically significant, we can ignore all of this information down here. And I'm going to give you more information about that in just a second. So my tunnel vision when I come to this output goes to the final assumption for running a repeated measures ANOVA. And since I see that the p-value here is 0.19, clearly greater than 0.05, the test statistic is 0.43. You can see that I've reported that here. Then Mauchly's test for sphericity is not significant, so the sphericity assumption is not violated. But what if it was? What if we get a p-value less than 0.05? Well, that's where things get kind of crazy. The other options, and this is right down here, sphericity corrections, all right, are the greenhouse geyser and the Heinz-Felt test. Um, Here's the way those work. We start with the greenhouse geyser, and you can see I'm working over here. If we look at the number of groups, in our case we have uh, 3 groups, but just think of K in general as the number of groups, okay? So 1 over 3 minus 1 is 1 over 2. So the bounds on the greenhouse geyser, this value right here, will never be smaller than, in this case, 1/2 or larger than 1. The 1, regardless of what K is, the 1 is always used. Now, our greenhouse geyser is 0.63. If you think about 0.63, 0.75 would be the mid-range from 1/2 to 1. So 0.63 is closer to 1/2. This means closer to 1 means that we have very little deviation from sphericity. Closer to 1/2 means we have more concerns with sphericity. It's really hard to say. So if we get something, past literature has said that if we get something less than 0.75, then we should uh, depend on the Heinz-Felt, this value right here. So here's where I think things are a little crazy. Okay, again, let's assume that this value is statistically significant. We get tunnel vision down here. Based on the value of the greenhouse geyser, we either report this p-value for our ANOVA, or we report, I'm sorry, this p-value for our ANOVA. Clear as mud, right? The p-value here has nothing to do with the greenhouse geyser and the Heinz-Felt. The p-value has to do with this p-value for our measurement. All right, so we don't have statistical significance. So therefore, I'm going to get this out a little bit. All right, so our attention comes to the ANOVA output. Specifically, we are interested in, for now, this line. Now, what does that line tell us? The ANOVA output for the within subject variable, the first thing we're given is the sum of squares for the measurement. And that's actually the sum of squares for the numerator. And in this case, it's 143.4. So we can think of that as our model sum of squares. Again, the sum of squares for the numerator. The 57.22 is the sum of squares for the denominator. We can think of that as the sum of squares for the residual or the sum of squares for the error. The degrees of freedom for the numerator is just k minus 1. Again, in this case, we had 3 levels, pre, post, and mid. So the degrees of freedom k minus 1 is 2. And the degrees of freedom for the denominator, as I've written down here, is just n minus 1, not cap n minus 1, not 18, but in how many measurements did we take in each of the segments. So for pre, we had 6 measurements. For mid, we had 6. And of course, for post, we had 6. We're going to have a balanced design when we have a within factor design because we're taking the same people and measuring them at all stages. So that's just going to be, in this case, 6 minus 1, which is 5. And of course, k minus 1 is 2. So that's where we get the 10. Now, the f calculation is just as before, right? The sum of squares for the numerator divided by its degrees of freedom. The sum of squares for the denominator divided by its degrees of freedom, 12.53. Now, the p-value, we should know by now that for the f, so 12.53, degrees of freedom 2 comma 10. So 0.0019 is the p-value. So this would be reported as, let's see, I thought I had it written out for you. Yeah, there we go. This would be reported as f 2 comma 10, 12.53 p less than 0.01. Now you'll notice something else that's pretty handy. The 0.167. It turns out that this is the effect size, and it turns out that this is the uh, uh, at a squared effect size. So 0.167, keeping in mind that the threshold for the small, medium, and large effect classification, 0.01, 0.06, and 0.14 respectively. So we are observing a large effect. So conclusion is there was a significant difference between measurements pre, mid, and post, because this value was less than 0.05 and a large effect was observed. And I'll show you how to write this up in a later video. Now, it's probably pretty obvious if you've been paying any attention previously to the other ANOVA models, ANOVA, two-way ANOVA, and ANCOVA, since we reach statistical significance, we are screaming for a post-hoc analysis. So all we know now is there's a difference between at least one pair of pre-post, pre-mid, mid-post, at least one pair. Well, the way we test that here is using the pairwise t-test command. And I want to start out with the score, and then over the measurement. And I want paired to be equal to true for obvious reasons. We have measurements on the same people. And I want the p-adjust method to be the Bonferroni. All right, so when we get this, we get only the p-values. We don't get as nice an output as we do with the Tukey HSD. But we get the p-values, and we can see that the difference in the mid and the post is statistically significant at the 0.01 level. And we can see that there is a statistically significant difference in post and pre at the 0.05 level. There is no statistically significant difference in mid and pre. So if these were a group of students, 6 students, for example, from the pre-test to the mid-test, there was no significant difference in the means. But from the mid to the post, there was, and of course from the pre to the post, there was a statistically significant. Sounds like one of my AirPods went, I don't know if you guys heard that or not, just went dead, so the audio may be a little wacky. I don't know yet. So because of that, I'm going to end this abruptly. Take care.